This is your rather late video now on the stuff for week 8. I believe it's week 8. I don't even know what day it is anymore. This is the stuff on momentum and impulse. So, we're trying to get grades in. If you owe us stuff, please try to get it done. A lot of my students owe one or two things, and then some of y'all, you're just going to have kind of have a plan to get it together, but it's okay. Anyway, we're doing momentum and impulse, and this is when we talked about forces. We talked about something causing the force and something feeling the force. Basically, if we have objects, let's make them carts. All right, these carts are going to be moving at some point, so we'll give them some velocity. And they're going to collide. They're going to interact. This could be cars colliding. This could be particles interacting, two electrons bouncing off of each other. It could be any sort of interaction where eventually I'm going to draw a free body diagram that has, so if I label this one 1 and this one 2, it'll have a third law pair of forces. This is going to be F by 2 on 1, and over here there will be F by 1 on 2. Right. And the idea is that F1, 2 is minus F2, 1 as vectors. Same size, opposite directions. And there might be other stuff. If these are carts, then you would also have normal forces and weight forces. And maybe you'd have friction. Right? But the other cart would also have these things. Right? Let's ignore friction. Let's just put in normal and weight. All right. So the result of this is a couple of possible things, but the idea is that all the forces I've labeled in black are what are called external forces. They don't count the two carts when we talk about their interaction. They don't, whatever these objects are doing to interact, the earth and the ground is not part of that. It's separate. So we just want to look at what's going on here. And this is the thing, is we can look at, we can look at this in terms of the velocities here, but there's something that we're not capturing here, and that's because they have masses, M1, here M1 and M2. So I want you to imagine a truck. You're driving in a truck and you see a bug come at you. So from your point of view and from the bug's point of view, you share the same relative velocity. All right, is the bug sees you coming at it at 60 miles an hour, and you see the bug coming at you at 60 miles an hour. Right? The combined speed between the two of you is the same value, but the effects are different. Right? You keep going no matter what, and the bug sticks to your windshield. All right? So there's got to be something that describes sort of how these third law forces result in future motion. And so what we do is we define the momentum. And we'll use the vector P is just the mass times the velocity vector. Right. So this lets us restate Newton's second law. And we're stating it in the way Newton actually said it, is that the net force on some object is a change in momentum over time. Now that doesn't seem like a huge deal here, because normally if I wanted to take this derivative, it would be d by dt of the mass times velocity, and the mass usually doesn't change. Right? All right. With this definition, if the mass is constant, you just get your original F equals ma. But that's not always the case. Sometimes the mass changes, like in the example of the truck and the bug sticks to the truck. Another example is rocket motors. As you burn fuel, you spit exhaust out the back. You're effectively changing the mass, and you have to account for that. So this is the more fundamental form of the equation. So we can rewrite this slightly. We can write it, and I'm going to write it in terms of differences instead of derivatives. I'm going to say that F is change in momentum over change in time. That lets us write F delta T is essentially m delta V. So this side is your impulse. That is basically how long is the force active for? Because that's something we haven't considered. We say that a force acts on something, we don't care how long it acts for. We assume it acts continuously if we're trying to describe, a continuous acceleration. The force acts as long as the acceleration acts. But sometimes we really care. The canonical example is hitting a baseball. Right? Is you can change the momentum of the baseball by hitting it really hard with a baseball bat. But you kind of have to consider how long the bat's in contact with the ball. So that's our definitions. This is what's called the impulse momentum theorem. All right, your impulse has to equal your change in momentum. So, we can do an example of that. Like, let's say you're trying to hit a baseball. All right, so there you are. Here's the other team in red throwing the ball. Baseballs are about 140 grams or 0.14 kilograms. And we will say that this baseball is being thrown at 35 meters per second. So after you hit it, there's going to be some speed outwards. And, if we look at a professional hitter, maybe this is 40 meters per second outwards. So in this, we haven't mentioned anything about how long the batter, let's put a bat in his hand. There we go. We haven't mentioned anything about how long the batter is in contact with the ball, with the bat. All right, so what we can do is ask what the impulse is. So what we do is usually give the impulse a label. I is F delta T, or something, this might also be J for some reason, but usually I use I, is F delta T. And from the impulse momentum theorem, this has to be m delta V. And so we can figure out what that is, 0.140 kilograms times, well, V final is 40 meters per second, and we're going to subtract off. It's going in the opposite direction. We're going to subtract off minus 35, so it's plus 35 meters per second. This is 75 times 0.14. 75 times 0.140 is 10.5, and then there's a matter of units. The units for momentum don't have a special name. They're just kilogram meters per second. You could also rearrange this if you put a seconds on top and bottom, Newton seconds. And that makes sense because the momentum, the impulse here is going to be in Newton seconds. Now, we can make an estimate of the time, right? If we watch a baseball game, like I don't recommend you do it, but if you watch it, it'd be hard to say that the ball's in contact with the bat for more than 1 or 2 frames. And a frame in video on television is like 30th of a second. So let's say a 15th of a second, that is 1 divided by 15 is, so let's say delta t is 0.067 seconds. Well, now we can find the force. The force is our change in momentum over change in time is 10.5 kilogram meter per second over 0.067 seconds. And that's going to be a big number. All right. Well, 10.5 divided by 0.067 is 156.7 newtons. Does that seem right? 156. No, clear. 10.5 divided by 0.067 is, okay, yeah, that's fine. So maybe our estimate's really wrong. Maybe this is too big. Because imagine what kind of force you think you could apply swinging a baseball bat. It's probably a body weight at least. It's probably 10 times this. Right? So maybe we're talking like, this is talking about 70 milliseconds. Maybe it's only like 10 milliseconds. Right? And so this will go up by a large amount. But anyway, you get the gist of how to work the problems. And there's nothing about this here that you couldn't go back and do by saying, well, let's just find an acceleration. All right, if we know the time and we know the change in velocity, you can find the acceleration. There's nothing wrong with that. But this is allowable for things where the mass also changes. Right? This is really delta P. It's not m delta V. Though most of the time you see it, it'll be this. Now, I do want to say that this is an average. Right? If we plot F and delta T, and we can put in kind of a weird shape here, right? Like say that's our force profile, right? Like you push on an object and you get a little tired and you push one more time and then you stop. Well, what we really care about is effectively what we're doing here is taking the integral of F dt. We're trying to figure out the area under this thing. Right? So there's our area. But what we really kind of want to do is just go ahead and smooth it out. And this is our F average, and this is our delta T. Right? So a lot of times we do that instead of trying to integrate an ugly function directly. And a lot of times we're not going to bother with impulse. So let's go on. Let's talk about collisions. Because what you really want to get into is what's going on with a problem when, right? So we want to deal with the collision we showed in this picture, the two cars colliding, or we want to do something like look at a ball bouncing. Right? So let's do an example of a ball bouncing. Right? So we're going to drop a ball, and we're going to drop it from a set height, say 2 meters. And it's going to come back to 1.5 meters. And so it's going to go down, and it's going to just jump back up. So nothing about velocities in there, but we could figure that out. Right? Now, the other thing is we're going to say something about the collision. We're going to say that delta t here, the time that the ball is touching the ground, is 20 milliseconds, is 0.020 seconds. So, again, there's not too much special about this, but we want to know the force that the floor provides to make it turn around. That's a useful thing. Is we're trying to figure out is essentially how bouncy the ball is, and so knowing how this thing interacts is important in it. So how would we do something like this? Well, first we can go around and deal with the energies and try to figure out what's going on here in this bouncing bit. And so, right, actually, we don't need to do energies. We can do kinematics. But you can do energies as well. Basically, the mass just cancels out. But what we have here is, well, the energy up here is mgh, and the energy here is mgh. And the energy at the floor is going to be 1/2 mv squared. I am doing this in terms of energy because you have a problem in the homework where we drop objects and we see how high they bounce. And at least the layout of the problem is going to look like this. You're going to do some other stuff on top of it. Right? So what we're going to do is when it falls down, we're going to say the energy final equals the energy initial. 1/2 mv squared is mgh, or v is square root 2gh. Right? Notice I didn't put the mass in there at all. And the same thing is going to happen on the other side here. Energy initial is energy final. So this is going to be V initial into the collision. And what we'll get from this is V final is going to be square root 2g h final. So we can figure out what those are. In this case, it's 2 times 10 meters per second squared times 2 meters is, this whole thing is 40 meters squared per second squared. And so V initial is going to be 6.32 meters per second here. In the other case, we're only going to go to 1.5. So 1.5 times 2 is 3. Is going to be 30 in here. And then that square root is going to be, V final is 5.477 meters per second. So we'll do 5.48. So the other thing is that this is falling, so it's negative. This is rising, so it's positive. And we probably need to put a mass in here at some point. We didn't put it here, but when we talk about momentum, we're going to have to put a mass in somewhere. So let's give this thing a mass and say it's 100 grams. So we're going to try to find this force. And we're going to use this impulse momentum theorem. Well, I mean, we can rearrange this. Well, we have 0.1 kilograms times, well, delta V here is 5.48 meters per second minus 6.32 meters per second. And all that's going to be over our time is 0.02 seconds. Now we plug and chug, do the work. 5.48 minus 6.32 negative, big number, divided by 0.02, and times 0.1 is, what we get out of this, we have kilograms, meters per second, that's newtons. We get 59 newtons. So I'm doing it like this. There's obviously ways that could be simpler. You could find acceleration. Effectively, that's what we're doing. That's the stuff in the parentheses here. But we want to consider that we're going to need to include our energy work with our momentum work in cases. There's going to be stuff going on where we want to figure out how to do collisions that make sense. So let's do some collision examples. So let's see. Let's put a card in. So 100 kilograms, that's going at 10 meters per second. And here's one over here that is going 6 meters per second, and it is 75 kilograms. Okay. Collide, and then we're going to let this cart return at 4 meters per second. Let's say. Don't know if that's a valid answer. We'll see. Now, this is the thing, is what's going on here. There's going to be this cart that we're trying to figure out how fast it's moving. And it might be moving to the right, it might be moving to the left. We don't know. But what we want to do is try to figure out how we can relate this motion before the collision, this motion after the collision. And so what's happening here, when I talk about other stuff like this ball dropping or this sort of stuff I've drawn out here, what's happening is there's an object, and then we're letting another object interact with it, and that gives us this force that arises between the two. Right? Or here, right, we have an object, and it interacts with another object, and we're treating them separately. But what we want to do is look at this and say, we're trying to figure out a property of both objects. We're going to include this. All right, this is our system. And external to the system is things like the earth, the ground that's holding it up, the weight force that's pulling it down. And those things aren't going to affect here. They're not going to affect the motion of these two carts. So if there's no external forces, then we can write that the derivative of the momentum of the entire system is 0, which means that the momentum is a constant. That means we can write P final is P initial for the entire system. So we sum up over everything in it that could be, let me rewrite this, this is the thing we're trying to say, and that means the final momentum of everything equals the the initial momentum of everything. Well, this we can just write out in terms of this and this, right? P initial is just going to be M1 V1 initial plus M2 V2 initial. And we can label these. We'll make this cart 1 and this cart 2. So we can fill in the numbers for this. All right. What we have is 100 kilograms times 10 meters per second plus 75 kilograms for the cart 2. And because it's moving to the left, it is, remember, these are all vector quantities. So minus 6 meters per second. So what we have here is 1,000 kilogram meter per second minus 300 kilogram meter per second is, our initial momentum is 700 kilogram meter per second. That's what we have to have later. So we can say P final is 700 kilogram meter per second. But that equals, now it's our mystery velocity times our mass, M1 V1 final plus M2 V2 final. And we only know this term is going to be 75 kilograms times 4 meters per second. And then we have 100 kilograms times V1 final is 700 kilogram meter per second. So this thing, 75 times 4 is 300. Oh, hell, I screwed up. 75 times 6 is 450. That means we have 550 left over. I'm not remaking the video. Please note, I'm just correcting this. It's 26 minutes in. We will practice more problems. If you don't follow it, just quit now. Or we'll come back on the next video. 75 times 4 is 300 kilogram meter per second equals, all this stuff. So what it is there's a total momentum here. This thing has, let's put it in purple, is 1,000 kilogram meter per second. This thing has 450 kilogram meters per second with a minus sign because it's going to the left. So between the two, there's 550. Between these two, there must be 550. So, but this one we show has 300. This one should therefore be 250. All right. And that's what we're doing. We subtract this from that. We have 250 kilogram meter per second is 100 kilograms times V1 final. And that means V1 final is 2.5 meters per second. And yeah, that's a lot of work. We're going to stop the video here because we're going to go through the types of collisions and some simpler examples. You see some of this in your notes. I'm just going to briefly go over the types of collisions, and then I want to get into some other information you need. So stop there.